We're in section 6.2, sine wave characteristics. Sine waves may represent voltage, current, or some other parameter. Most commonly, we'll be looking at voltage. The period of a sine wave is the time from any given point on the cycle to the same point on the following cycle. The period is measured in time, and in most cases it is measured in seconds or fractions thereof. The time of a 60 cycle second is 16.667 milliseconds. So if we took, if we said 1 second and we divided it into 60 parts, then we would get the time, and here this would be the time of 1 cycle, and hence 1 period. And we could look at a circuit simulation, and here we would have our single, the period of 1 cycle, and this actually came from our previous lesson. Remember, we started out with 1 volt at 60 hertz, and this is the resultant sine wave, and the time from right here to right here, that represents 1 period, and we can see the time readout right here, 16, it's about 16.5 milliseconds, should be 16.6. I guess we could have, our measurement points are not quite perfect, but you get the idea that 1 period, if we're going at 60 hertz, is 16.6 milliseconds. Okay, frequency. The frequency of a sine wave is the number of complete cycles that occur in 1 second. Frequency is measured in a quantity called hertz. 1 hertz corresponds to 1 cycle per second. Frequency and period have an inverse relationship. We can say that time equals 1 over frequency, and that frequency equals 1 over time. And we just, actually on the previous screen we did this. We said 1 over 60 equals it was 0.01666. Actually, that's how we would read 16.6 milliseconds, but on a calculator it would come up looking like that. And that's the fractional equivalent of 16.66 milliseconds. And also frequency equals 1 over time, so if we took that value and we said 1 over that value, 0.01666, we would get 60. So time equals 1 over frequency, and frequency equals 1 over time. Frequency to period and period to frequency conversions are common in electronic calculations. Peak value. The peak value of a sine wave is the maximum value or current it reaches. This is the value you would read on an oscilloscope, and we had when we previously looked at that signal, the peak value would be at this point, right, that'd be the positive peak, and this would represent the negative peak. Peak voltages occur at 2 different points in the cycle. One is positive, one is negative. The positive peak occurs at, and this is 90 degrees, and the negative at 270 degrees. The positive and negative have equal amplitudes, and we can quickly look again at our simulation, and we can see that the let's take a little, and here we have it. Here we see this is the peak value at this point, and then this is the negative peak. And this is at 90 degrees, and this is at 270. This is 360, and this is at 0. Okay, average values. The average value of any measured quantity is the sum of all the intermediate values. The average value of a full sine wave is 0. The average value of 1/2 cycle of a sine wave is, and this is the average of 1/2. So if you're looking at a sine wave, and if we were to average every single point on this entire wave going both positive and negative, well, we're going to result in this. We're going to have it's going to be 0. But if we averaged every point on the wave on just the positive side or just the negative side, we would find that the average of all of these values is this fractional value right here, 0.637. So if we wanted to calculate the average value of the peak wave, we would simply take it, and again, if we started out with that voltage of 1 volt, if we took 0.637 times 1 volt peak, well then our average value is 0.637. Okay, RMS value. One of the most important characteristics of a sine wave is this RMS, or oftentimes it's referred to as its effective value. The RMS value describes the sine wave in terms of an equivalent DC voltage. The RMS value of a sine wave produces the same heating effect in a resistance as an equal value of DC. Okay? The abbreviation RMS stands for root mean square, and is determined by, and here we have a formula, 0.707 times the peak value, and that is in voltage. If it's current, it'll be the same thing. The RMS current, or excuse me, the peak current times 0.707 will give us the RMS current. The derivation of this formula is addressed in upper level courses. For our purposes, we will simply use it as a method of converting between RMS and peak. And so let's take a look at our simulation. In our simulation, we showed the sine wave of 1 volt peak, and we had 1 volt from 0 to the peak value here, and 0 going to the negative peak. Now, we also have a multimeter connected into the circuit, and this is for discussion for purposes of RMS. And notice the oscope is connected across this 1 ohm, or this 1 k ohm resistor, and we're measuring 1 volt peak and 1 volt negative. This would be 2 volts peak to peak if we were looking at it that way, but typically we say 1 volt peak. Now, we put our voltmeter across the same place in the circuit, across the same component, and notice, and we're measuring this, we've selected AC, and you'll notice the reading is 0.707.071 millivolts. And that correlates to our calculation that the values that we just looked at. Remember, we said the RMS value is 0.707 times the peak value. So we had looked at that previous signal, and we saw that we had 1 volt peak to peak, or 1 volt peak, and then we took 0.707 times that value, and that gave us the RMS value. RMS values for voltage or current, and this is just a review. If you take peak times 0.707 will give you the RMS value, or you can take RMS value divided by 0.707, and that will give you the peak value. Or you can say RMS times 1.414, and that will give you peak. And so if we said, with this, we already did this one, we started out with 1 volt times 0.707, and obviously we got 0.707 volts. Then we took, or we could take the RMS value, and now that would be 0.707 in this case, and divided by 0.707, and that would equal the peak. So 0.707 divided by 0.707, that's 1 volt, which was our original value in peak. Or we could take RMS times 1.414, and if we took 0.707 times 1.414, we would get 1 volt. Most voltmeters are calibrated to measure in RMS. So when you take a voltmeter, a VOM, or a digital multimeter, and you measure an AC value, you will measure the RMS value. Oscilloscopes display peak or peak-to-peak values. And this is, I've alluded to it already, but another measurement used to describe sine waves are their peak-to-peak values. The peak-to-peak value is the difference between the two peak values. And so here we have the first peak, and this would be our positive peak. This is our negative peak. And if we're measuring from here to here, then that would be our peak-to-peak value. And so when you're doing oscilloscope readings, typically you refer to either the peak value or the peak-to-peak. And obviously peak-to-peak is going to be twice the value of the peak. And that concludes section 6.2.